Okay, finally, let's go through a worked example of some synchronous design. Essentially what we're going to create is a small state machine where we actually go through and work out our flip-flops and how we design these things and use some Carnot maps. So we're going to design a synchronous state machine that will count down from 5 down to 0. So we've got 6 different states here: 5, 4, 3, 2, 1, 0, and then it will repeat. Now on power up, we don't know what state it's going to go into. It could go into any state. If it happens to start at state 6 and 7, we want to assign it so that the next state that it will jump to after that will be state 5. So it puts it back into a known state. So we're going to draw a state machine for this, a timing diagram for 8 clock cycles. We draw each of our states here, and we'll show how these link between each other. Show what happens for state 6 and 7 as they feed into state 5. Now, having this state machine that we've got here, this state transition diagram, we can draw a truth table based on that. So essentially, we can list down the side there the number of the current state that we're in. We need 3 flip-flops to encode this because we've got 6 states in total. If we had 9 states, for example, we need a 4th flip-flop to encode those. But here we've got 3 flip-flops, and what we need to work out is what the current state is compared to the next state. And we can read these straight off our state transition diagram. So if we're in state 0, 0, 0, state 0, the next state we're going to get to is state 5, because remember, we're counting down from 5 to 0 and then looping back to 5. Likewise, if we're in state 1, so 0, 0, 1, the next state that we're going to be going to, and the next values that are going to be going into those flip-flops, will be 0, 0, 0, state 0. So we can write that in our current state and our next state in our truth table. What we do then is we need to develop a Carnot map for each one of these next states, AD, AB, and AC. And if we develop a Carnot map for each of these, we can determine a minimized logic expression to implement each of these. So here are our logic expressions. I won't go through the full details of the Carnot map, but we've got a logic expression now in minimized form for each of these. And you'll notice, particularly for BD, we've got a number of isolated ones, so they're in full sum of products form. What we should be able to do now is very simply draw a circuit diagram. In this case, we've got D flip-flops, and we've implemented our logic there. In this case, we haven't used a NAND gate form or anything like that. We've just implemented our logic based on what we calculated from our Carnot map before. And we fed that back into the inputs of each of our D flip-flops. So from the AD flip-flop, the B flip-flop, and the C flip-flop. And then we've got our clock that goes into each of these flip-flops because it's a synchronous design. What we'll do then is final step of the timing diagram that we asked for at the start. So here's our waveform diagram. What we see here is we've got our values A, B, and C, and as each of these count, we see the new value that's going to be supplied to AD, BD, and CD. And we see these basically 1 clock cycle behind the values that we see in A, B, C above. So here's our 8 states that we've got here.